3, the yellow region. Now, the yellow region is way more chaotic than the orange and turquoise regions. And you're going to see why in a minute. They're just more complicated. So these nuclei are too heavy to be stable, since they are above lead 82. And so what you find here is that in this case, the fastest or the quickest way to stability is not to lose one neutron, not to lose one proton like in beta decays, is to lose neutrons and protons quickly. So in this case, what do they do? So if you have an alpha decay, what you find here is that you lose 2 neutrons and you lose 2 protons. So that's really quick here. And so what you're seeing here, if these guys are too heavy, you're finding here is that this reduces the mass the fastest way, fastest possible way. But what you're going to find here is that now let's go look at the, you know what? I should have moved. I'm going to move this a little bit. I'm not changing anything. All I need to do is I want to put in the band of stability here to show you what do I mean. And I'm going to move this up here. And what you find here is that what we're going to look at is that we want to look at one region in particular, okay? So note that there are really 2 regions, okay? There's a region right here. Okay, and then there's another region. Now I'm going to be careful here and look, there's like a little channel here. Let me show you what I mean. I'm going to take this and I can't blow this up this big here and then keep it, but I want to show you what I'm looking at right here. So I'm making this thing huge. And what I really want you to pay attention to is I look at that there's this orange region right here. And then there's a channel right here. And then you'll see that then I get the yellow region. There's some green in there, but that's pretty natural, but you're going to see that's quite different. It's this channel region that I really want to pay attention to. And you know what I should do here is that I should make a copy of that. I don't need to have the whole graph. I just want that little channel. So I'm going to delete this now. Okay. So if I delete this, look what I'm going to do here. I'm going to put that little channel and then I want to make this bigger. Now, what's one of the things that I really want you to think about, I guess I should put this down here, is that now if I sort of like redraw the whole thing, what you're seeing here is that there's a little channel here. And then it goes like that. And so in this situation, the reason why we're seeing what we're seeing here is that these nuclei are what? They're too heavy to be stable. That's why it's in the yellow region here. And so what we're going to find here is that what I'm going to look at is one particular situation. I'm going to look at decays of particles that go down this channel. And so what you find is that many of the particles, so many of the heavy nuclei, heavy unstable, stable nuclei are coupled with alpha, beta, both kinds of betas. Oh, I'm sorry. Coupled with alpha and beta decays. Okay? They're coupled together. And what I really mean when I say coupled is that they form decay chains. They form decay chains. And sometimes you'll hear people in the business call them series. There's a series of decay chains, but I think the decay chains is really clear here. So when I look at this thing, I mean, this is kind of the way it is. The way it is here is that any atom above lead is unstable. So any nuclei above lead is unstable. And we've discussed this numerous times. But what does this mean here? What that means here is this. All heavy nuclei will eventually reach lead after a series of decay chains. And I'm going to tell you, this is really complicated. This is something that I would never ask you to do in like a quiz or an exam. But I think you should really understand this because, I mean, one of the things, there was a guy by the name of Claire Patterson, and I talked about him and his importance in finding that our environment had a lot of lead contamination. And he is the result of removing lead from gasoline, paint, children's toys. And what he did here is that he was looking at particular isotopes of uranium. And when he was looking at these particular isotopes of uranium, he knew that uranium was heavy and unstable and that it would decay. So as it decays, it goes towards what? It goes towards lead. And as it goes towards lead, you can actually measure the age of the Earth by knowing how much lead is in a rock. It's a really fascinating story. And, he's a fascinating guy, but this is really not the place to talk about him. So all heavy nuclei eventually reach lead after a series, right? Because they're all radioactive. So this is why I'm making that statement. And so what we're going to do here is that we're going to look at a decay chain that follows right here. So what we want to do is we want to start at uranium-235. So here's what we know. So if you follow the work of Claire Patterson, here's what we know, that in the Earth's crust, there are a few long-lived isotopes of uranium. And we're going to look, by the way, another one that really shows up a lot is thorium too. So these are things that are really studied here. So the two that we'll look at is that we'll start off there's 235 uranium, and the other one is 232 thorium. So if I look at these guys, where are they at in the table here? Well, I'm going to take a guess is that this guy, uranium-235, is going to be somewhere about, well, it's got to be heavier than thorium. So because thorium, why is it got to be heavy? This is 92 and this is 90. So what we want to do here is that we want to go in and we want to look at these guys. So if you look where they're at, so that means they got to be above 92, 82. So I'm going to say that this is what you find. You're going to find that thorium is probably going to be about right here. Maybe I should do this in black to really make it stick out. So right here is thorium, around that. And so the other one that we're looking at here is we're looking at 235, which is higher. And so this is 235 uranium. And so what you're going to see here is that uranium and thorium are going to decay. Now, remember what I said here. So when I look at these decays, what you're seeing here is that, look at the turquoise. This is the region of beta decay. Look at the orange. This is the region of inverse beta. So what you'll see here is as uranium-235 goes through here, this guy has to go through not only alpha, but sometimes it lands in the beta region. Sometimes it lands in the inverse beta region. So there's a series of decays that actually start to occur. Now note, this is complicated. So let's go look at uranium. So what I'm saying here is we know that, so let's focus on our example here. So we want to look at the 235 decay chains. Okay, that's going to be our example here. So if I look at the decay chain, then that means I have uranium. And if I have uranium, then that means I must have lead. So if I look at lead, we know it's got to move in that direction. So those are the important two elements here. Okay, these two elements are the important ones. So now let's go look at what happens here. So this is complicated, and I don't want to scare you in any shape or form, because I would never ask you to do this. But this is what we're going to find here. We know it's got to go towards lead. And so we have 235, 92 uranium. And so now we have a series of alpha, beta minus, beta plus decays. And eventually they have to go to what? 207. Now remember, there's 3 or 4 stable isotopes of lead. So it could be 207, it could be 208, it could be 209. In this case, it's going to 207. So what I want to do here is that I want to show you at least one decay chain where I'm going to be careful here. So let's look at this thing. So I'm going to draw a graph, and I'm going to try to be nice and clear. And I don't know how this graph is going to come out. So give me a moment to see if I can get this to come out. So I know that uranium is 235. And as it goes to alpha, it reduces its mass. So that means by 4. So I got to start counting by 4s. So then this is 231, 227, 223, right? 219, 215, and I got to keep going. And then this guy's got to be 211, and then finally I get to 207. So note that these decrease, or they change by 4 because alpha decreases mass by 4. That's why I did that. Now what I'm going to do here is that I'm going to have this one here. And I'm going to go that this guy here is going to be 82. And then I'm going to go to 84, 86, 88, 90, 92. And I just wanted to make it nice and tight, because I think this is really hard to draw. And so this guy right here is the atomic number. So here's what you're going to see here. If I do alpha decay, this thing has to fall. So what I'm seeing here is that this square right here is a unit of 4, and this square going this way is a unit of 2. And that's because an alpha particle is 4, 2. And what it does here is it removes 4. And then this guy, it removes 2. And then if I look at a beta inverse particle, a beta decay increases protons, whereas an inverse beta decay decreases protons while keeping the mass the same. So here's what you find. If I do an alpha decay, it's going to be 1 full square. If I do a beta decay, well, that increases the number. So then you're going to see that I'm going to come in with the green and I'm going to go half a square. And then inverse beta decay goes the opposite direction. So in this case, it goes that way. Now, again, this is complicated, but we don't need to look at the details. I just want to show you one. So here we go. We know we have 235 uranium, which is right here. This is 235 uranium, and it's going to decay. Where does it decay to? It's got to go all the way to 207 lead, right? This is 207 lead. So there's a series of decays. And so maybe what happens here is it goes something like this. It goes this way. Oops, wrong color. It goes this way. That means that it's an alpha. And then it may go, in this case, if you're looking at the channel, look at the channel. So if you look at the channel, if I'm going through this channel, note that I could be going along alpha, and if I alpha, then may drop it into beta decay. So then all of a sudden it moves into the turquoise region and it goes back. So that's beta minus. And then maybe, so now beta minus then brings it back down and it does this type of thing. And what you're seeing here is that I'm seeing a series of decays. Maybe it goes like this, and then this guy goes like this again. Or maybe now it falls into the inverse beta decay and it goes this way. And then all of a sudden it goes beta decay. But what you're seeing here is that I'm working my way down. And maybe now I hit another beta decay and then it does alpha all the way to here. Or then maybe it goes through a series of, oops, wrong color, a series of alphas, not alphas, beta, and then it just keeps moving down like this. And then maybe it does another one like this, and then finally it reaches all the way down. Complicated. Not easy to do that, but that's what it means by a decay chain. And what we're seeing here is that we're actually seeing this picture right here. This is exactly what you're seeing. So when you look at 235, and we're seeing this decay chain, it's looking like this. So what you're seeing here is, let's say here that this is 235 right there. It's actually higher, but for our purposes, it looks like this. So what does it do? It comes in here, and maybe it goes like this. And then all of a sudden, it goes into here. And then it comes back here. And then it comes out here. And then it comes back here. Then it goes in here. Then it goes here. So there's these series of decays that are happening. And we'll say that right here, this is 207 lead. And eventually it gets down to there. And now this is the black line of stability, which that's where it rests. It's now stable. That is complicated, right? I could say the same thing with a different atom. And in this atom, I could come over here and I can look at, oops, sorry about that. Clicked on the wrong window. I was going to get another image that I have that I wanted to show you. We could then have thorium. So then if I look at thorium, this time I won't go through that torturous process here. But if I look at, then I have lead right here. And so what you're going to see here is that one of the very famous ones that Claire Patterson did in aging the age of the Earth is he looked at 232 thorium. And this is unstable, of course, because why? It's above lead. And what you get here is that you get, again, a series of decays, which we will not do that again. And in this case here, it does go to lead, but it goes to a different isotope of lead. And so what you're seeing here is that now I have a complicated process. And look at this. This is a decay chain. This is the way you see them in nuclear textbooks. You can see here is that this is our start right here. And then here, this is the end. And so you could see I start with thorium, and you look at all the alpha decays, right? Here's alpha, 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 alpha. And you could see that we're going through many, many alpha decays. And then we have combinations of, in this case, beta decay. So if I follow this decay, what am I seeing here? This time I'm going to bring the whole graph. So now that we've talked about this little alleyway right here, I'm going to use the big graph to show you exactly what I'm seeing in my mind. So here I go. So what I imagine, I start here. I'm starting right above the alleyway. And in this alleyway, I have 232 thorium. And so when I look at thorium, this only has decays. It only has what? It only has alpha and beta decays, not beta inverse decays. So that means it never enters into the orange region. So now if I go look at lead, that's lead right there. This is 208 lead, a stable isotope. So what is the decay chain going to do? So to get there, it never enters into the orange region. It only goes to the blue and yellow, blue, yellow, blue, yellow, blue, yellow, like this. And so it's only between the turquoise and the blue region. And that's why alpha decays are very complicated, because of all these possibilities that can occur.